So, good morning everyone. I'm the last presenter. I'm the one who is standing between you and lunch. It's a good thing. I see it as a positive thing. I'm not the last person between you and leaving the conference. Going back to the discussion that we had before for Ahmad, there are two different sets of requirements, reliability side, between buildings and bridges. And I think Ian mentioned it very nicely. Bridges are designed for 1,000-year return period for functionality. Buildings functionality is designed for a much lower return. So you get a less strict behavior for the building side on the buildings. What I have for you today is on validation of simulated ground motions. We have been blessed with peer funding and Caltrans for that matter for the bridge side since 2008. These are a list of projects that we have been working on since 2008. We started with looking at the behavior of skewed bridges with ET at UCLA. And the latest work that we have done for Caltrans is on guidelines for ground motion modeling for performance-based quick engineering of bridges. We have developed a tool, it's HATSIM. The person who developed this is Jawad sitting in the middle of the audience. You basically put the latitude and longitude and the site characteristics of your site. Push a button using the site-based approach, and what I have for you is a test for validation of physics-based simulated ground motion, which I'm going to go through for today. You can download this tool and some other tools that we have developed at Irvine at that website. So with this, the partners in crime for today's presentation is Jawad again. All the curses goes to Jawad, the glory all comes to me. Or the other way around. We are working with Mesa Dabawi and her graduate student Sarah Azar at the American University at Beirut. We are using physics-based simulated ground motions. We could not have done the work without SCAPE, which is the Southern California Earthquake Center. These folks are the owners of the physics-based simulated ground motions. They have the tools, they have the know-how, and the technical activity group, which is titled Ground Motion Simulation Validation. As part of SCAPE, we get together every 2 weeks. The work that we're doing here and other work funded by SCAPE is being communicated, so we have also used their advice and inspiration that we get from those presentations. All that cannot have a peer presentation without showing the trade. IM, intensity measure, the EDP, the damage measure, and decision value. What we have been doing so far in all this peer work is using NGA West 2 ground motions. This is a picture that I got from the work that Campbell and Zareian did for their GMPE, the attenuation model. Horizontal axis shows rupture distance, vertical axis shows magnitude. You can see that in the large magnitude region, you have a lot of data for long distance, you don't have much for the short distance. Plus, if you're living in the 21st century, although the administration of the country is not living in that area, but that's totally fine. We want to make things tailored. We want to have tailor-made ground motions for the region that we are doing the design for and the building or bridge that we are working with. So we are moving towards using simulated ground motions. So with this, I would like to talk one slide about two different ways of simulating ground motions. One is called the site-based. You can imagine that you are standing at the location of a bridge or building. You know that the magnitude something happens at the fault at a certain distance. With the stochastic process, starting from the work that Van Mark did in 1976, down to the work that what Armin Derkurabian and co-workers, Zareian and Mesa Dabawi have done in the past recent years, and the work that USGS folks have done, Steve Hartzell and co-workers, there is a way of doing site-based simulated ground motions. We have used these site-based simulated ground motions to do the HATSIM project that I showed a small icon of it in the beginning of the project. The work that SCAPE folks are doing is using a physics-based simulation. So basically you have the fault model, rupture model happens, it moves in the 3D medium and comes to the site of your liking. This is basically, the physics-based part is very deterministic for long period motions, or you can call it the low frequency. The high frequency, low period side of the motion is still done in a stochastic way. You merge them together and you have a complete motion. Our job is to validate them for you. This slide is the beginning of the philosophical conversation of what is validation. You have reality, which is up here. You think about the conceptual model, and then after doing a lot of work, you develop this computerized model. A validation job is to see how much this computerized model can replicate your reality. So two things come, two key issues for validation of simulated motion. It should not depend on who has done the simulation or what model you have used for the simulation. An analogy is you want to have a test to see how much chlorine you have in the pool. It shouldn't matter who put chlorine in the pool or what manufacturer you bought the chlorine from. The second part, depending on the engineering application. Once you build the test, it matters if you want to validate the simulated ground motions for bridge application, usually high frequency bridges. These are low period bridges. The bridges that we are having in this project, between 0.6 seconds period between 1.11 or 2. Or you want to do this for tall buildings, which goes to the periods of 3 or 4 seconds. Now it comes to the steps to do the validation. Again, philosophically, you want to identify few validation parameters. You want to find what is the best estimate to find those parameters, see if the simulation set gives you similar results, how close is close enough, we have a good, bad, ugly, and eventually you can make a judgment. So with this, I think I will start talking about what we have done so far in the whole process of validating simulated ground motions from the get-go like 10 years ago. We first started by looking at waveforms, the wiggles. How the wiggles look similar to each other. We're done with this. The next two parts, which I'm going to start off talking about these RZZ parameters, which I would like to call them a more sophisticated way of juicing a waveform into a vector of tiny parameters. We try to look at scenario-based validation. You have Northridge, in reality, they are picked up at the stations. You have a simulation of Northridge, you pick it up at the same stations. The difference between the behavior of the structures, which can be an SDOF or an MDOF, can show how good, bad, or ugly your simulation was. Again, with regard to these, we have done publications in 2010 and 2012. Coming down to the next two parts, D and the E part, which is the current trend, work that Jack Baker, Stanford, and John Stewart at UCLA have done. You want to look at the previous data and form a ground motion prediction model. The ground motion prediction model is right now between event parameters and SA. Now we can think about event parameter and proxies. You want to use, and these are those parameters that you're going to use for validation. Jack Baker used the ratio between rod D100 to rod D50 and a few other parameters. What we are using are what we call the RZZ parameters. I have one slide about what are these RZZ parameters, but you can think about them as how you can juice a waveform, means acceleration in time, into duration, areas intensity, dominant frequency, and the rate of change of frequency of the ground motion. It can get more elaborate than that, but we do today, and with the time that we have, I think is good enough. The last part, which is again another school of thought for validating simulated ground motions, would be how about I just simulate ground motions and I put them in a database, like the way that I have done with the NGA West 2. I'm going to use this simulated set to select and match a target spectrum. That is a totally different way of doing things, and Greg Irvine and us, Stanford and Irvine, are doing the work in this area. Now let's move towards the problem statement for the peer work that we're doing here. First, can we develop a validation test for to validate simulated ground motions? And the answer so far, based on the one bridge that we have used, is yes, but we need to do a little bit more to make sure that our test is good. And ultimately, use that test to see if the physics-based ground motions from SCEC are good enough. So these are two things that we want to do. This is to be done. We are moving in this area right now. Our approach. This is the part that is really hard. I'm sure that you guys have a lot of questions, but just bear with me. This is the part that if you're not listening so far, please listen to what I'm going to say in the next 5 minutes. The blue dots, the pale blue, are the stations that CyberShape, a way for simulating ground motions by SCEC, has done the simulations for. They have simulated all possible scenarios that you can imagine in Southern California. It's a huge database. The red dots are stations that I have information from previous earthquakes. The dark blue is where these guys have the match. So what I do is that I'm going to get statistics of the magnitude and distance of the recorded set. This is what nature has given me. I have one of nature. If I can rewind Earth, do again, I'm sure I'm going to get many more, but I don't have that opportunity. I don't have the capability. So I'm going to use this one set. Given the information from SCEC, I can generate 100 catalogs of the past 150 years ground motions in the same area. And I look into their distribution, and they look more or less similar. So now I have one from nature and 100 catalogs from simulations. I would like to see how these guys fare to each other. So moving forward, keep that there. I need to bring in a few other parameters, and then we're going to put all of these guys together. I would like to talk about an EDP. We only look into column drift ratio, but we build the column drift ratio similar to rod D50. We're applying two components of the ground motion. We rotate them every 90 degrees, and we get the median value, and we call that the rod 50 CDR. This is very similar to rod D50, and that's the EDP that I'm doing a validation for. Or cannot have a presentation without showing a model. You guys can see the model once the presentation goes on. Talking about the RZZ parameters. This is two components of the ground motions. For the presentation here, imagine that you are seeing this one guy. These two plots will start moving when the animation starts. You're going to see this black dot moving up and down. Every time that the black dot crosses 0 up, you're going to get one added as it goes forward. And this is the area intensity that's going to happen. And here you go. The animations are a little bit slow, but as you can see, as time passes, this guy is going up, and the 0 level up crossing starts building up. So let's close the slide and go to the next one. Once it's completed, I'm talking about the RZZ parameters, the parameters that I want to use for validation. Areas intensity, duration. I'm going to fit, okay, I need to talk about this T-net, coming to the 30% areas intensity and marking this timestamp. This basically says what is the time that you are in the middle of the strong motion. At that timestamp, you're going to come to the 0 level up crossing second order polynomial that you have fit to it. And the slope here is the dominant frequency of the ground motions at T-mid, and the rate of change of this slope, which is the second order, is the rate of change of the frequency. So with all of these RZZ parameters, now I get to talk about what I'm doing for the validation. I have three domains. The domain of event parameters, everybody is familiar with it, magnitude, distance, site characteristics. RZZ parameters, for each motion you have a vector of areas intensity, dominant frequency, duration, etc. And ultimately, what is my EDP? I would like to form three black boxes, or you can call it three processes. The process that takes magnitude, and distance, the event parameters to EDP. The process that takes event parameters to my validation test. And what takes my validation test to the response parameter. I'm arguing that if I do the fitting between these guys and EDPs within the 101 sets, one set from recorded will give me one set of coefficients, 100 set of simulations will give me 100 set of coefficients. I'm saying that if the one recorded falls, or each coefficient falls within the plus minus 2 sigma of what I get from simulations, I am getting the ballpark correctly. Let me repeat this with another way of presenting the philosophy. If I can redo Earth, I can get 100 recorded catalogs. I can't, I only have one. If I have done the simulations, I have 100 of them. If the distribution of simulations, this recording happens to be plus minus 2 sigma of it, I'm okay with that recording. So let's talk about what actually this means. This is a slide that we added just this morning for presentation. When I say what I mean, the recording happens to be in the plus minus the 2 sigma of the simulations. These are the coefficients that we get when we fit the black boxes. The green is the center of the simulations, and the yellow is where the recording coefficient is falling. If this guy is close enough to this, up to plus minus 2 sigma, we're saying that you're good. Now, yes, I think I'm done with MB advice. So the first part of the process is, let's see if these simulations are valid. That means I have moved from theta to EDB using my simulation set, and theta to EDB with my recording set. I have realized that magnitude and distance and fault characteristics and hanging moment and all of that coming to EDP, the coefficients are very similar from plus minus 2 sigma. That means that the simulated ground motions through sketch, the cybershake simulations, are good enough. This is established right now. The question is, how can I tell an engineer to use this? I cannot ask an engineer each time that they want to validate simulation methodology. They run these 100 catalogs of simulations into the bridges that they have, and eventually see that they're going to give them the service. So they say, I'm okay with what I have already. So what we do is to see if these RZZ parameters are sufficient. So the next step is to see if these RZZ to EDPs work, and the equation shows the EDP is a function of functions of Ayres density, middle frequency, the derivative of the frequency, and the duration parameter. And this nicely shows that, again, those guys are also falling between the plus minus 2 sigma, so they are equally sufficient, and the coefficient and the R squared for this equation is around 0.8. That basically means that these RZ parameters are sufficient enough to represent the process, and if the simulation, and they are equal with the simulation and the recordings are equal on that map. The last part of the process would be, and the derivative of the frequency, you're good. Plus minus 2 sigma shows to be accurate more or less, except that it misses in a couple of places, which basically shows that these RZ parameters are too good, too straight. This is the end of the work for this one bridge that we have done, which is bridge B with a period around 0.8 seconds. We're going to continue this work for the bridge A, C, and F with the periods of 0.6, and 0.9, and 1.1 second. We're going to use the broadband platform simulation. This is another slew of simulations that SCEC has. It's different from CyberShake. In this one, you control where the hypocenter and the magnitude can be. So one level of approximation moves away. We're going to simulate the same catalog of the recorder once we do the broadband simulation. And eventually we can build the test and do the work. And with that, take your questions. Thank you.
Okay, one question, two questions? Anybody have a question?
Would the same kind of evaluation be done on the site-based?
Sure. As I mentioned, philosophically, we spent a lot of time making sure that the philosophy of the validation is accurate. A validation tool, it's correct or is basically acceptable if it does not matter who did the simulation or how you did the simulation. It should be free of that. So we definitely can use the site. Actually, Jawad and I were talking about this, that we really probably need to do this for the site simulation.
How do you set the threshold to say, well, okay, it's valid or not?
So the idea is this. Do I have a few minutes to talk about this? Because it goes down to the philosophy. There is no straight answer, but baby, let's go to this black box and I hope it just waits here. All right. I think this is good. All right. Event parameter to EDP. I have 100 catalogs, that means 400 ground motions, maybe 300 ground motions of simulations. So this means that I can make this equation 100 times with 100 different forms of coefficients are going to come. There's going to be a coefficient for magnitude, there's going to be a coefficient for distance, all of those things. but I have only one recorder. Can I say that if I had the opportunity to rewind Earth and read it, I would have had 100 recorded? At that point, I could make a comparison between the distribution of the coefficient from the simulator and distribution of the coefficient from the recorder. But I don't have that luxury. I only have one from the recorder. So I'm arguing that if that one happens to be the plus and minus the sigma of my simulation set, that gives me only like 5% chance of missing. It should be good enough. By the way, there's a very nice YouTube video that says, how did this 5% test of significance come by? Which was basically the guy who built this says, I think I'm comfortable with 5%. Actually, Eduardo Miranda has a paper who argues about this.
If you go back one slide, just backwards to, I think we saw one of your 5%. Go back one more. Just to your
I'll
plus.
try. So forward.
Was it forward? Sorry. You had one where it was outside of the 2%, so you didn't point it out, but it's there.
Oh, you mean that is just an in-house slide. Let me,
We actually
Yeah, bottom top. Right, so bottom right.
bottom right, this is one that will get failed.
Okay, so
So-
you're allowed to have 5% outside of that.
If it falls outside, but we have to remember, this particular work is done for areas intensity as a function of event parameters. So there's a lot of them. And in this one, it fell out. The test of significance for this guy, it shows that in 42 out of the 899 that we did, this parameter was not significant. So I'm actually not going to look at CLO.
Okay. Well, we're into the lunch hour. So.
Yeah, I know. Sorry, guys.
But not by much, so that's great. Let's thank the last speakers one more time.
Thank you.